empty data structure, and if you have insert, you can create the data structure anyways. So these three are seen as fundamental operations on most data structures. It doesn't necessarily have to be for everyone. And if you know how to do them well, then you've got the data structure figured out. Now, different data structures have different characteristics in terms of time complexity. So if you have an unsorted array, it's very hard to search because it's not sorted, but it's easy to insert or it's easy to delete some specific item. Unless delete requires you to first search it before you delete it. In that case, it might take long. A sorted array has, you can speed up the search, but insert now becomes very expensive because you can only insert at a specific place if you want to keep it sorted. So remember, here we are looking at dynamic data structures where things are constantly changing. If you don't care about changing, static data structures, it's a very different deal. So here we are focused on dynamic data structures. And so that's with the arrays. With linked lists, you have some similar things. I don't want to go through all of these. But the important thing is these binary search trees. If you have regular binary search trees, the great thing about it is that search, insert, and delete, all three are of time that's proportional to the height of the tree. And the height, of course, for a regular binary search tree is not guaranteed to be log n. All you know is that it could be anything. And in fact, in the worst case, it could be as bad as a skinny long tree. So it could be as bad as big O of n, which means that binary search trees are good, but not great. They can behave badly. So that brings us to balanced binary search trees, which says that you can do search, insert, and delete all in log n time. That's why they are important, right? So your basic operations that you perform on the data structures, they're all super efficient. And you can prove that you can't do much better than this for worst case search. Okay. In fact, this is some kind of a lower bound, and so in some sense, the balanced binary search trees are optimal. And you can prove that you may be able to speed up one of them, but then you will end up paying for the other. So it's always a trade-off. If you try and speed up, squeeze a little more time in one, you'll end up paying for something else. Okay. So in some sense, this is roughly the best you can achieve. However, it only does the three basic operations: your search, insert, delete. Okay. Now, what if I want to add more things? That's where all of the interesting stuff comes up, right? What's happening here? Yeah. So this is the red-black trees, and you're pretty familiar with this. This is an example of a balanced binary search tree. And as you know, red-black trees will guarantee you height of roughly log n. In fact, it can never be more than 2 log n. And that gives you the time complexity for search, insert, or delete. Okay? So this is all good. But then, if you start to ask range queries, our goal is to ask more interesting queries, not just search, insert, and delete. We want to know how to handle more complex queries. So the first interesting one is something like a range query that says how many items in this tree are between 6 and 14. Okay. Now remember, this is a query where you have no idea what range you're going to ask. You're going to provide an A and a B, and your job is to quickly tell me what is the number of items between A and B. So your variables are A and B. That'll keep changing. And for every query, you need to answer this for me as fast as possible. Now, so the question is, how fast can I do this? Well, there is a simple answer where I could just look through all the elements and do this in linear time. You'd like to do this faster because you've spent a lot of time building this complicated tree. The question is, how much faster can I do? And it turns out that you can answer this query in log n time. And the reason you can do this is because there is a simple operation that you're going to be able to perform. Can you pass me that pen? Thanks. We have an operation called the rank operation. So rank of x and something called select of k. These are actually complementary operations. The rank of x says, I give you a set of items, somewhere here is x. Your job is to tell me what is the rank of this guy, which means if I put them in sorted order, where does it stand? Okay, so that's what rank is. Select says, I'll give you a certain rank, and your job is to find me the kth smallest item in the set. Okay, so here you're given an item and you're asked the rank. Here you're given the rank and you're asked the item. So so these are complementary operations. Now it turns out that you can solve this problem quite efficiently with a little bit of work, and I'm going to show you that. But if you're able to solve this, can you now solve the range problem? Okay, so this is something that I want you to think about.
One question that I have is that I have no idea what this data structure is, but it seems to me that this specific type of tree, the left element is smaller than the node.
That's right. So yeah, you will see this in the data structures class. It's basically a binary search tree with some extra features added to it. So it's actually, so a binary search tree simply has, on the left it'll be smaller items, right is larger items. So it's exactly what you just said, but it's a little bit more than that. Okay. It guarantees that the height is reasonably small. And that's why I said, that's why I showed you the previous slide. These red-black trees are, this balanced binary search trees. Red-black trees are an example of a balanced binary search tree. So it falls in this category where it guarantees search, insert, and delete in log n time. Clear?
So what is the specific?
Yeah, it'll take me a full lecture to explain this. But right now you have a package in Java or C++, Python. You can download code for red-black trees, and it's fairly straightforward. So right now, let's just think of it as a black box. Okay, some other time, or you'll see this in class sometime, and you'll learn it. For now, we don't need to get into the details. We are trying to see how we can improve on the questions we're asking, namely, let's make sure we can do basic operations very, very efficiently, and then let's slowly start to add additional operations and do them well. Okay. So as I was saying, the next one that comes to mind is what's called as a range query. A range query says, I will ask you, I'll say, give me range x comma y, which will say, tell me how many items are between x and y. Okay, which is what that query is. How many items are between 6 and 14, right? So it turns out that you can answer range in terms of these operations. And how will that turn out?
Rank of 14.
Yeah, so it'll be rank of y minus
rank of x minus 1.
Yeah, so there's a 1 that'll show up. It might be plus 1, is it? Well, it depends on whether you want to include x and y, things like this. So let's just say it's roughly rank y minus rank x. Okay. If you include x and y, then it'll be plus 1. If you don't include x and y, it'll be minus 1, things like this. So anyway, you can figure that out, right? So range is essentially the difference in rank. Because if you put them on a sorted list, then x will be sitting somewhere, y will be sitting somewhere, and all you need to know is what the index is. Well, there are other minor issues here, and that is x may not be in the set, y may not be in the set. Same thing over here, x may not be in the set. You still want to know what would its rank be if x were in the set. Okay, Hey, Demba. You'll get minor issues here, and you have to worry about is it there, is it not there. I don't want to worry about all that stuff, but the point is that roughly range can be written in terms of rank, which means if I can do this efficiently, I can do range efficiently. Clear? Now, there are actually other kinds of range queries, but we'll get to that in a minute. The select operation turns out to be almost very similar to the rank operation, but let's see how to do the rank operation. Now, in order to do the rank operation, here's the thing that we're going to plan. Yeah, thanks. Let me see if I have a slide on this or not. Yeah. So this is the same tree as before. Okay. The only difference in this tree is that we've added some extra information in each of the nodes that tells you what is the size of the subtree underneath it. Here, this is a leaf, so therefore this subtree has only one node. This also is 1. This is also 1, 1, 1, 1, 1, 1. But now if I look at this node here, you have a subtree that has 3 nodes in it. And so this guy's information here is 3. If you look at this node here, the information is 2. This one has 4. That one has 9. Up there is 17. So the information at the root of the tree tells you how many items there are in this tree. Right? Now, this is called the size information. So let's say that in each of the nodes, I add this extra information called size and store it there. If I were to do this, it turns out that I can solve the rank operation quite efficiently. And it takes a little bit of code in order to kind of figure this out. So actually, let's so let's say that you want to know what is the rank of 13. Okay. Now, how do I figure this out? Well, I know that there are 17 items in this entire tree. So the rank cannot be more than 17. But then I also know that the left child has is a root of a subtree that has 9 nodes in it. And since x 13 is smaller than 20, it's somewhere in this subtree, right? Which means that its rank, the rank of 13 is in the big tree is the same as the rank of 13 in this tree. And so I am going to now restart the search, but from this node. Okay. Then when I come down here, I find that I want to know what is the rank of 13 in this subtree, but 13 is bigger than 11. And this node here has a left subtree that has 4 nodes. I don't need to go and look at it. All I do know is that it has 4 nodes. If I include this, it'll be 5. So definitely 13 is bigger than 5 of the values, which means its rank is going to be more than 5. And so I can then restart the process and find its rank in this subtree, but add the ones that I've bypassed, which is 5. And when I come down here, I'll go through some similar process, and I'll figure out that the rank of it over here is 2. And so therefore, there were 5 items here plus the 2 here. That'll give us a rank of 7. And it turns out that whatever I just described can be written down as a recursive program in a beautiful manner, and you'll get rank really, really easily. So the code, where is that code? I didn't write it down, sorry. We can actually do it here. Yeah, I can hopefully write this on the fly. So let's say that I want to do rank of x in the subtree rooted at y. So this is going to say report the rank of x in subtree rooted at y. Okay. So the way I'm going to do this is as follows. I'm going to say if y if the value stored in y, or if the value of x equals the value of y, equals, then it's quite easy for me, because y, remember, y is the root of the subtree, right? So if I am here and if I'm looking for 11, then what is the rank of this? The rank of this is one more than the size of the subtree, of the left subtree. So, so I'm going to say return size of left subtree of y plus 1. Okay. So this is if x is equal to y. There are two other possibilities. Value of x is smaller than value of y. Value of x is larger than value of y. And so those are the two cases we have to take care of next. And I've run out of space here, so I'm going to use up this part here. Next thing we're going to say is if value of x is less than, strictly less than the value of y, then we're going to simply return the rank of x in the left child of y. So we're just going to look at the left subtree. Okay. Otherwise, we know that the only other possibility is that the value of x is larger than value of y. We've taken care of equals, we've taken care of less than, so the only other possibility is it's larger, right? If this is so, we're going to return the rank of x somewhere. What's that going to be?
Right.
Oh, sorry, I didn't write this properly. So this should say return rank of x in left of y. Even here, no, here it's correct. So here I have to say return rank of x in right of y. So now we're going to go to the right subtree because we know x is larger than y. But then we're only going to end up searching here, but then we have to count how many items we bypass to the left. And what's that going to be? Plus size of left of x, left of y plus 1. So all of this is going to. So this code is really quite trivial once you understand it, but the recursion takes care of everything here, right? So this is the general idea. There is one other case you have to worry about, and that is if y is nil. If y is nil, you have to return 0. Okay. So I need to put that in somewhere here and say if y equals nil, then return 0. So mostly this code is just trivial. You can pretty much whip it up in a few minutes, right? Everyone okay with this? Okay. So I've told you how to create rank, assuming that every node has this extra information called the size. So that's why this is called an augmented red-black tree. Okay. Now, magically, when we added this size information, we were now able to solve rank operation. And you can quickly look through this code and figure out that the rank operation also can be executed in time proportional to the height of the tree. Because we start there and either we go left or right, left or right, left or right until we reach the node. So therefore, the time complexity is log n, which means that we can now go back and say some wonderful things. Remember this table we made. We said that search, insert, and delete could be done in log n time. But now we've added a little bit of information extra, and suddenly we can add rank to be performed in log n time. There's a similar thing you can do with select. So let's say that we go back to the same tree and we say, I want to select the 9th largest item here. Okay, so assuming that the size information is there, how do I do this? Well, I know that the root of the tree, its rank is 9 plus 1. So therefore, the root of the tree has a rank that's larger than what you're looking for. You're looking for the 9th item, so therefore, you've got to search in the left side. So you go down to this T here and say, I'm going to look for the 9th item. Well, we know that the 9th item is going to be the largest item in this tree. So it's easy to find it now. It is going to be this guy here, but maybe that was too easy. So let's try the seventh largest item. Okay. So if we want the 7th largest item in this whole tree, 7 is larger than the rank of that guy, so it has to be on the left side. Over here, the 7th largest is not going to be in the left subtree because the left subtree only has 4 items. It's not the root of the tree, so therefore it must be over here. And we bypassed 5 items, so therefore we want the 2nd largest item in this subtree. And to find the 2nd largest item, we know that this subtree has 2, so it must be over here. So we come down here and say we want the 2nd largest item here. This guy has rank 1, so therefore the 2nd largest must be on the right side. So we go down here and look, and ultimately this is a leaf of the tree, so this must be the 7th largest item. Okay, so all we did was to traverse the tree from top to bottom, from root to leaf, and therefore its time complexity is proportional to the height of the tree. So therefore I can do rank and select operation both in log n time. So this is the beauty of the solutions, assuming now that we have this size information. Now, adding size information makes the red-black tree code a little more complicated. And again, you can find code in Python, Java, or C++ to take care of the size information. Any questions? Because I'm just talking and talking. You're all good? So I'm not giving you the details. I'm not telling you exactly how to add this size information. In fact, there is also, you also have to go and change insert operation, because when you insert an item, all the size information could change. And so we have to figure out how to update the size information as you insert. When you delete items, again, these numbers may change. You have to know how to how to fix this. So it turns out that what we did before for search, insert, and delete may have to be modified in order to take care of size information. But as long as size information is there, magically it's going to help us to solve rank and select. And if I have rank, we know that we can also solve the range problem, right? Because range is simply the difference of ranks of 2 items. So now suddenly we have a lot more things that we can solve efficiently. We could do search, insert, and delete, but now we can add rank, select, and range. Yeah.
You can still add the size, and all the operations will still be in log n.
That's right. Yeah, everything will be log n, not n log n.
Oh, okay, yeah, log n.
Yeah. Okay. So that's, and as I said, you can find code for this. The standard red-black tree code will probably have it. If not, you may have to search a little bit harder, but it's there. So we've managed to add 3 new operations, all of which can be solved in log n time. Okay, and one of them was a range query, was a range operation. Now the range operation, there are actually 2 or 3 different versions of it. Let's see if I have that here. So yeah, we've gotten over here. You can see here that this was what we had before, search, insert, and delete. But now I have rank and select, both of which can be solved in log n time. And I really should have added one more column here. That's the range operation. That tells you how many items are between x and y, and that's simply finding two different rank values and doing a subtraction. So, so this is called a one, right. So actually, let me back up one second. I could ask you other questions. I could say, list me all the items between 6 and 14. Okay, how am I going to do this? And how do I do it efficiently? Well, I know I can count very, very fast because I can compute the ranks. And so therefore, I can do that counting in log n time. It doesn't matter how many items there are in between, but I can count in log n time. But if I want you to list them out, then is the time complexity still going to be log n? Why not?
I mean, you're bounded by how many elements there are.
That's right. So if the range has a lot of items, if you give the smallest item and the largest item and say, list me all the items between them, you have to list out all the items, and there could be n of them. So therefore, to actually list out the range of the set of items within that range can take you a long time. However, if you do the analysis carefully, then we're going to call this the list range operation, which is list out all the items between x and y that are in the set. Okay. So in this case, it turns out that the time complexity is actually k plus log n, where log n is the cost of finding how many items are in this range, and k is the number of items in that range. Okay. For each one, you're going to spend at least a constant amount of time. Now, if you don't do it carefully, you're going to end up with k times log n, because once I know the range of the left end and the rank of the left end and the rank of the right end, I can use select operation and say, okay, give me rank 6, rank 7, rank 8, rank 9, rank 10, and I can use the select operator for this. But that's going to be expensive because that would be k times log n, right? But in reality, I can actually do k plus log n. And the way that's done is by adding some more information here. And what kind of information would you like to add in order to make that k plus log n? Everyone understand the question? Understand the problem here? How should I fix this data structure in order to print out everything between 6 and 14? But I want this done efficiently. I want to spend only constant amount of time per extra output, but I can spend an extra log n time to know where to start and where to end. So the idea here is, any thoughts?
So what information do you have? You already know where to start and where to end.
Yeah, I know that I need to start at 6. I can go and find that in log n time. I know I have to start in 14. It's not here, but I roughly know where it is.
And then you want to print out everything between 6 and 14.
Right.
Just something, I know it's not what you're looking for, but let's say we find the smallest element, and then the extra information we keep is like the next pointer to the next node.
Right.
Order.
That's right. So you could add some extra information called the next pointer. So the next one for 6 would be 10. Next one for 10 would be 11. Next one for 11 would be 12. Then would be 13 to 15 to 16. So it's following the in order traversal. Right? So you can do a quick in order traversal, add all these extra pointers, and that way you can always get to them. Now you have to be a little bit careful about adding extra information, because you have to make sure that your previous operations don't get messed up. You have to make sure that your insert and delete operations still work in log n time. Well, if you want to insert a new item, and if you know it's the items on either side of it, then you can go and fix the pointers. If you're trying to delete an item, if you know it's previous and the next one, again, you can go and fix it. So you have to be a little bit careful. If you keep track of both the next and the previous pointers, then you can fix it a lot more easily. So that's definitely one solution. There are other solutions, but the next and previous pointer is completely fine. Okay, so I am now adding size information, and I'm also adding next and previous pointers. And if I do this, I can achieve listing out everything within a range in k plus log n. Is that clear? All good? You do have to be also anyway, I don't want to get into those details for now. So what we've managed to do is solve one of the hardest range query problems in one dimension in roughly log n time. This is essentially the size of the output. There is no way to skip this time complexity. So k plus log n is pretty efficient. Okay? Any questions? Okay, so what we have done so far is to solve the one-dimensional range query problem. If I give you a set of values, and I ask you A and B, give you A and B, and I say, tell me how many items there are between A and B, or list me all the items between A and B. This is how you solve it. Okay? What was I going to say here? Right. What you need to understand is that you can insert and delete things, and it can still answer that query in the same amount of time. So you could say, oh yeah, I'm going to insert a bunch of things, I'm going to delete a bunch of things, and I will keep, in between I'll ask you for a range query. Then I'll insert some more, I'll delete some more, and then I'll ask you another range query. You should still be able to answer them in this time complexity. And the good thing with this data structure is that it's completely dynamic, which means I can do insert, delete, search, range queries, list range, anything, all in the most efficient time possible, because I'm going to keep track of a bunch of information in the tree and make sure that these operations are facilitated efficiently. Is that clear? Yeah. So we've now solved the one-dimensional range query. By the way, you may be able to find code for this and things that are a little more efficient than what I described. You could save on the number of pointers you store in each node, or something along those lines, and improve on the time complexity. Okay? All right. Now we're going to look at, we can talk about another problem there, which is in your, I've talked about before. But instead, let me spend some time on something else. Yeah?
Can you use like this to replace like a segment tree or something like that?
So segment tree keeps track of segments, right? And those are ranges. And that has a slightly different flavor. So you're asking, if you had a segment tree, can I replace it with something like this?
Yes.
That's what you're asking. So there may be way too much bookkeeping that it's not worth your while to convert it. But there are problems where you can forget that you can solve this using segment tree. Instead, you could solve this using range trees. And I'll show you some examples. In fact, if you prefer to talk about that, I can talk about that. But I wanted to quickly touch upon two-dimensional range queries, because that's what you've seen recently, and it's quite it seems to show up quite often, right, in these competitions. And I think I hinted upon this, the solution a little bit earlier. So let's see what's going on here. So what's going on here is, think of a real number line. Assume that, remember these are values here, and this is somewhere here is a 0, right? This side is plus infinity, this side is minus infinity. If I take any set of items, these items essentially look like points on this line. Right? So I can think of the set as a set of values on set of points on this number line. And your query simply says, if I give you a range on this line, your job is to tell me which items are in this range. So I have A here and B here, or I think I used X and Y, it doesn't matter, A and B is fine. Your job is to tell me how many items are here, or your job is to tell me which items are here. And the way we did this was we took these items, put this into a red-black tree on top of it, stored it there, added some extra values on size and pointers, and then we were able to answer these range queries pretty quickly, right? Now I want to generalize this problem to 2 dimensions. Okay, so imagine now that instead of points that all sit on a line, so instead of thinking of these as values, think of them as points on a line, right? Instead, we're going to now think of points in 2-dimensional space. So imagine that I have a 2-dimensional space, right? I have an x-axis and a y-axis, right? And imagine that I have a data set that has a bunch of points. These are my points. So every point in my data set has x coordinates and y coordinates. Now, I can think of doing searches. How do I do a search for a point? I ask you, does your data set have this point 2, 3? Does your data set have the point 7, 1? And this involves doing a search. Now, how do you do that search? That's one question. How do you insert points and delete points in such a way that you can do search quickly? Then you could ask more interesting questions called range questions, where I could say, here is a range of y values, here is a range of x values. I want you to tell me how many items fall in this range. So instead of A, B, I now have A and B for the x-axis and A and B for the y-axis. So I have AX and BX, and I have AY and BY. And so your job is to tell me what falls in this range. So we need to know all the things that fall in this rectangle here. Is that clear? So this is called a 2-dimensional range query. All right. So you're given an x range and you're given a y range. And since all your items have both an x coordinate and a y coordinate, your job is to find things that fall here. Now the question is, did any of the things we did that we did for 1 dimension, can that be generalized to 2 dimensions? Right? And this problem shows up in many different ways in many problems. It's quite interesting. So this problem, in fact, is not so trivial. I'm going to show you how to modify this data structure in order to take care of that. Okay. So we built what are called as 2-dimensional range trees. Now 2-dimensional range trees are quite interesting. In a 1-dimensional range tree, we take all the x values and put it into a standard red-black tree with all the additional information that we talked about. So then we can answer queries in X quite easily. So one approach could be do the range query for x. So take ax and bx, find all the things that are in here, and then search through this and find all the things that fit your y description. But then it's possible that there are a lot of points here. It's possible that all the points are here. Okay? And so if you have lots of points, you'll end up wasting a lot of time looking at things that don't end up in the final answer. And so your time complexity depends on how many things are in your x range, when really all you needed to see was the x and y range. So that brings us to something called a two-dimensional range tree, where this is your standard red-black tree of all the x values of all the points in this data structure. And then this tree, of course, has nodes. Every node is a root of a subtree, right? This subtree has a bunch of items, and all those items are going to be contiguous in your data set, in your data structure, right? But they are contiguous in the x coordinates. So therefore, this might be some range over here. What we're going to do is at each node, we're going to build a second data structure, which is going to be the same set of items that you have here, but sorted by y coordinates. So we're going to use the y coordinates to build a different tree of the same points that are here. And we're going to do this for every node in the tree. So every node will have a shadow tree that's going to be built using the y coordinates. But the main tree is going to be built using x coordinates. Okay, so this is going to be a tree on the x coordinates, and there are going to be lots of these trees built on y coordinates.
Can a point appear in multiple y trees?
Yes, because that's obvious, because this guy has two children, right? It's possible it has two children. Each of those corresponds to a subtree, and those subtrees will have shadow trees, and so therefore all the things that show up in this tree are also in this tree.
In that case, how do we bound the space complexity?
Correct. So there's space complexity, there's time complexity, there are all sorts of questions. So let's start with space complexity. Yeah?
Is this approach much better than that approach that was discussed?
Right. So it turns out it is, because in the worst case, if I first take the x range and then go and search the y range, it's possible that the x range was just a dummy, and it gave me everything. Okay. So in the worst case, I'm going to end up with the entire data set, when really the y range was the important range. If I decide to focus on the y range, maybe again it'll get me everything, and maybe you should have focused on the x range. There's no way of knowing what query you're going to get, and there's no way to decide whether that strip, whether it's vertical or horizontal, has a lot of points.
Yeah, right.
And ultimately, you want the time complexity to be, so the desired time complexity turns out to be something like this. You want something that you're forced to expend, okay, plus the time complexity should depend on the number of points that are actually going to get output. You don't want to look at a whole lot of garbage.
Yeah.
Okay, that's where the problem is.
I see. And that's still a problem, even though you can search for both ranges.
That's right. Yeah, even though you could do lots of little tricks and heuristics and say, oh yeah, if you're getting too many points, don't do this, blah, blah, blah. That's not going to help you, because it won't give you a general solution that works for all ranges.
I see.
Okay.
Yeah, I was thinking maybe it's possible you can do both the X and Y searches.
So for instance, I could make the Y range, even though it's big, it could be completely empty,
Yeah.
right? And your X range could be any size. you're going to end up spending way too much time.
Wouldn't you just spend log of n time?
No, it depends on how many items are in the x range or in the y range, and not in the intersection of the two, right? So you got this y range, you got this x range.
Yes.
If you take the union of this, that could be a lot of points, but the number of points here could be dramatically smaller. Could be, in fact, empty, for all you know, right? And that's where the problem is. All right, so the question is, this idea sounds good, but it sounds crazy because it's just duplicating all sorts of things. Points are showing up many places. Aren't you just spending, isn't your space complexity way too high? Well, in order to see that, let's look at any item, any single item, and ask how many different shadow trees does it show up in? Okay. In order to understand that, remember that the height of this tree is log n because we are looking at balanced trees. So here is a path from root to leaf. That path is how long? It's log of n roughly because that's the height of the tree. So therefore, any point here is only going to show up in all those, well, in some of those trees. So therefore, every item can show up in at most log n trees, and therefore, your space complexity now has gone from n to n log n. Fine? Then, let's talk about time complexity. So in time complexity, what we said initially was, if you just worry about x range, I can do this in log n time. Forget about the k for now. Let's say we want to do a count. Okay? I just want to count how many items are there, and I want to know how long it takes. So if I only focus on the x range, I know I can do it in log n time. If I only focus on the y range, I know I can do it in log n time. But now I'm focusing on both x and y range. How am I going to do this? Let's assume, for the sake of argument, that this node itself is the perfect range. Okay? The smallest item is where the A starts, and the largest value is where the B ends. Okay? So therefore, all you want to do is to search in, is to count how many items are in this subtree. Yeah, so therefore, this is exactly the same as this, and so my search becomes just searching how many items are in the y range, and so therefore I can do this in additional log n time, right? Because none of these trees are more complex than the original tree you started with, and so therefore I can get to here in log n time, and then I have to spend another extra log n time to take care of this, right? In reality, it's a little bit more complicated than that, because when you do a to B range, it's not going to be in one node, it's going to be in a bunch of different nodes, right? And let me show you what that means. The picture looks something like this. Actually, let's go to the example because that'll make it clear for you. Yeah, here it is. So let's say we want to go from, what do we want to do? Let's say we want to go from 6 to 31. Okay, just to make the problem clear to you. So 6 through 31 will end up looking something like this. We know that 6 is to the left of 20 and 31 is to the right of 20. So this is a key node, right? Then actually let's go from 6 to 13. I think that 6 to 13 is a better thing to work with. So therefore, we'll start at 20. We know 20 is irrelevant because both 6 and 13 are on one side, right? And so we'll go down to 11. So 11 is a key one because 6 is on the left side, 13 is on the right side. Then I'm going to focus on 6. So that's going to be 10 here, 5 here, and then 6, right? And on the other side, I have 15, and then 12, and then 13. So I want to know how many items are in this range. I haven't drawn the entire tree. Anything over here is irrelevant, right? Because I only need to care about the node where that has both the 6 and the 13, the A and the B, and the left and the right end of the range there. But then I have to do some extra work because there are there could be a bunch of things over here, right? There could be a bunch of things hanging off of here. There may be a bunch of things over here, but that's not relevant. Here you have taken care of both. There may be a bunch of things over here that's not relevant. And there may be a bunch of things over here that are not relevant, but there may be a bunch of things here that are relevant. And there may be a bunch of things here that are relevant. So I have 4 different subtrees that I have to take care of, okay, in one way or the other. And each of those is going to have a Y shadow, right? And they have to be accounted for in some way or the other. Yeah?
Why is the right side of 13 not relevant?
Right side of 13 not relevant because it's outside the range.
And then, oh, okay, sorry.
Right? We're looking at 6 to 13. That's why left of 6 is also not relevant, right? Okay, so so now what we're going to do is in fact, these 4 trees are the only trees I have to worry about. I will go to their Y shadows, pick up the Y range, and pull out the things that work for me. These green pieces here are all completely within the range, right? Because it's larger than 10, but it's smaller than 11. This is smaller than 12, but larger than 11. This guy here is larger than 6, but smaller than 10. And this here is smaller than 13, but larger than 12. So all these guys have things that are in the X range that we are interested in, but then let's assume that we also have a Y range that we are given. I don't know, Y1 to Y2, right? Or Y left to Y right. Let's call it Y1 and Y2. Is that clear? So now I want to know how many are both in 6, 13 range for X values and this range for Y values. So I'm focusing on this first, but when I focus on this, I get a bunch of subtrees plus a bunch of nodes. So I'm going to need this node, I'm going to need this node, I'm going to need this node. That's not going to be in my range, this is in my range, and this is in my range. Is that clear? So I am going to look at these starred nodes, and I'm going to look at all these green subtrees that I drew here. These are my only places where I may be able to find things that fit this range. Now, how many nodes did I put stars on? I took one path to 6, so these can be at most log n of those, right? I took one path through 13, that's another log n of those. So there are at most 2 log n nodes I'm going to star. Then how many green shaded subtrees do I need to worry about? Remember, there's only going to be log n of those on this side and log n of those on that side. So at most 2 log n such subtrees that I have to worry about. So I'm going to search in each of these subtrees, and then I'm going to look at all the starred nodes. Whichever ones also fall in the Y range, those are my interesting nodes, right? So I have to now set it up so that I search all those. And how do I search here? Very simple. Go to the shadow tree and do a range search for Y. Is that clear? So I'm going to go here, go to its shadow tree, and do a search for the necessary values of Y. I'm going to do that for this, I'm going to do that for this, and I'm going to do that for that. Okay? And then all the starred nodes, I'll quickly check whether their y values are relevant. And so I will, and these are the ones I'm going to output. If I'm just counting, I'm going to spend log n for each one of these, and I'm going to spend constant time for each one of those. So therefore, the total amount of time I spend is
Log squared.
log squared n. Does that make sense? So the time complexity is not k plus log n, but it's actually k plus log squared n. Was that too fast? Okay. Did you understand how it became log squared?
Because you have at most log.
You have at most log n trees, are actually 2 log n trees, and in each one you're going to spend log n time to do a y range search. By the way, this is called a 2-dimensional range search. You can find code for this somewhere, and all you do is plug it in.
So the first time, the 6 and 13, that was just one dimension of the search, right?
Correct.
So
the main tree is going to be on x.
okay.
The shadow trees are all on y.
Okay, and each node in the main tree has a shadow tree
Correct.
with all the way.
Now, I don't want to go to the entire shadow tree of 10 because there are parts of it that are not in the range,
Yes.
right? So, but if I look at this green shadow shaded subtree, it's completely in that range. So I only want the ones that are completely in that range, go to its shadow tree, pick up things that are relevant. Otherwise, I'm only going to do single nodes, and that can be easily tested in constant time.
And while searching in those shadow trees is when you actually get the values you want.
Correct.
The first search is just to narrow down the range of shadow
Correct.
trees you want.
That's right. Okay. So this is your standard 2-dimensional range search.
So we compare it to the approach where you try everything within that range.
Yeah.
We're going through all the x values, but
Yeah.
we're not going through all the y values.
Yeah.
That's how it works.
If you do that, so here is a simple way to do this, right? You stay in this tree, forget about the shadow trees, right? You stay here, you find all the things that are in the range 6 through 13, and then for each one of them you check whether the y value is right or wrong. The only problem for that is you're essentially taking everything here, and then you're saying, let's go through each one and figure out which one falls in the y range I want.
So the time saving happens on the y values.
Yeah, you could say that. Yeah, because, well, I could always start with the y values,
Yeah, whatever
and
you-
then, yeah, whatever you start with, that's where you're going to save time, because that's your standard data structure. But the shadow trees are also exactly the same technology, same approach, right? Yeah.
And then to code this, you would like maybe have like use the one-dimensional one and use the in-order thing.
Yeah, well, the whole thing is just a copy, right? It's just that you have to tell it what value it needs to be indexed on. Is it the x or the y?
Yes.
Everything else is the same.
But-
And what is the set of values that it's representing?
But you do need the nodes to keep track of like that.
Well, sure, there is a set of items, but that set of items is already in the tray.
No, what I meant is that you need to keep track of like the nodes, like for instance from 6 to 10, from 10 to 11, from 11 to 12, 10 to 13, which is like the select thing that we discussed.
Well, that's because if I give you this problem to answer, how are you going to do this? Well, I'm going to start with the x values. The x range is 6 to 13. So my first job is to locate 6. So I start at the top and then locate 6. So all the things along this path are of interest. Wherever I do wherever I do a left, I will star the item. And wherever I end at the item I find, that also has to be starred. Otherwise, I only star the things that go left. I'm sorry, that where you're not going right. Okay, so yeah, where you're going to be going left. So that's right. So this and this, you're going left, and so therefore you're going to include that.
As long as it's
Yeah, and on this side, I will do the exact same thing, but I'll search for 13, but I'll only keep track of things where you're going right. Because if I'm going right, I'm going to be left with a tree hanging that I have to search. Right? Yeah. So yeah, the coding is not trivial. This is why you go there armed with the code. Right? There are lots of details here, and it's worthwhile for you to even try coding this yourself and seeing how this works out. And I'm sure it's worthwhile for you to do it once if you want to. But you could just, if you don't have the time, you just plug in ready-made code. Why bother? But you need to understand how the heck it works. Otherwise, you're not going to get very far with it. Now, if you recall, there was this one nice problem where we said, find me all the things. Well, you're given 2 points, and it says, I will tell you what range of angles to look at from here, and I will tell you what range of angles to look at over here, and your job is to find me everything that's in between. Okay, this was the strange, interesting problem that we looked at. Okay, how am I going to solve this? Very simple. I take this point and I sort all the points in my system with regard to the polar angle subtended here, and then do a range query on that. And that'll give me a range. That'll give me all the points in this sector. And then I'm going to do the same thing with the other point, but use that like a y coordinate. Right? So essentially I get everything in between. Is that clear? So there are lots of interesting problems you can solve with this range query stuff. Just amazing. All you have to do is decide what's your x coordinate, what's your y coordinate, and I could do even instead of it. So these are 2 angles, right? I could also do everything from here, but that's within a certain distance range from here. How would I do it? So I'm saying find me all points that subtend a certain angle range with this, but also at a distance range of 7 to 10. How would I handle that? Well, I'm going to get a second range that looks like this, right? And now I want to find all the points here. So again, you can take the distance from this as your y coordinate. So depending on the problem, you can decide what your x coordinate and y coordinate are, and you'll do all sorts of interesting regions, and you can count them. So that's 2-dimensional range queries, right? I'm almost out of time, so I'm going to tell you a couple of problems, and then you can think about this. Right. So in this problem, actually forget about this. I don't want to show you that. So here's a problem that's there in you'll find it somewhere in the data set, in the problem set. You're given a sequence of numbers, okay, and these sequence of numbers are increasing. Or rather, these sequence of numbers are non-decreasing in the sense that it may be equal, but it will never go down. Okay, so it could be something like 1, 2, 2, 7, 7, 7, 8, 9, 14, 14, 14, 14, 19, 23, 23, 23, something like this. Okay? And I'm going to give you a list like this. And your job is to, so and then I'm going to say, hey, here is a chunk of this list. Find me the most frequent item here. And you're allowed to pre-process your data. There's no insertions or deletes, but you have to pre-process this data so that any range I give you, you answer it quickly. Of course, there is a simple way of doing it. Start here, look at all the items, count it, find the largest one. No big deal. But clearly, you don't want to do that. So how do I turn this into a range query type problem? So it turns out this is a range query problem. Okay. Any thoughts on how you would approach this? Is it a range query? Yeah. Sorry?
I'm not sure, but it's because I mean, you could put the frequency at each node.
Uh-huh.
But then wouldn't you just check to see, which? Oh, I guess you still have to check in the range. You have to check all of the. Yeah, you have to check all of the nodes in your range.
Yeah.
And check the frequency.
But how do you do all of this efficiently? If you start with this, then this could be very, very large, whereas the number of items could be relatively small. Yeah.
Still make a binary search tree,
Mm-hmm.
but include 2 pieces of information. So we only store unique values in binary search tree,
Okay.
but you store frequency
Yeah.
of that value, and then also the
Yeah.
most frequent in that subtree.
Okay. So the maximum in a subtree.
Yeah, and the maximum in the subtree. And then we can kind of do the range search like we did before.
Yeah. So you may also need for each item you may need its index range in the original set.
Yeah.
Right. So did everyone catch that? Let me explain what Ricky is suggesting. So the idea is we turn this into something else. So first of all, let me write down the indexes. So I have 1, 2, 3, 4, 5, 6. So I have 16 items here, right? I am going to turn this into a new array where I have 1, I have 2, I have 7, I have 8, I have 9, I have 14, 19, and 23. So only the unique items are in the list. Okay? For each item, I am going to store the range of indices it's present. So for instance, this guy is present from 1 to 1. This guy is present from 2 to 3. This one from 4 to 6. This one from 7 to 7, 8 to 8, 9 to 11. Sorry, 9 to 12, then 13 to 13, and 14 to 16. Okay? So we have this, and now I'm also going to add to it the frequency of each of these guys. So what's the frequency? Well, 1 shows up 1 time, 2 times, 3 times, 1 time, 4 times, 1, and 3 times. Okay. So if I ask to go from location 5 to location 9, okay, then it'll only include 2 copies of 7, but only 1 copy of 14, right? And so the most frequent item would then be 7. But if I extended it a little further, the most frequent item might be 14. So it'll keep changing depending on where your range is, right? So roughly speaking, the tree will start to look like this. Here are the items in your data set. Each one has a frequency associated with it. Okay. And then your job is to do the search on this. I did add the range of the locations, but you can actually infer it back later if you want. So how do I use this? Do I have anything more here? Yeah. So there are a bunch of different queries that one could ask. One could ask, what's the frequency of 15? Well, if I want the frequency of some item, all I have to do is to go and look it up, right? 15 has 15 has 14 copies according to this, right? Then if I want the most frequent item between 10 and 16, here the 10 and 16 are actually the item range, not the index range. So if I'm only going to ask that kind of query, I don't need these ranges here. I only need the item and the values. So between 10 and 16, which one is the most frequent item? Again, you go back here, and you know that it's going to be this or something out here, right? And as Ricky was suggesting, at each node, you have both its frequency and the highest frequency in its subtree. So for instance, the highest frequency here would be 7, highest frequency here would be 7, here it would be 11, here it would be 14. And here it would be 14. So when you do the search, you can quickly figure out just by looking at the root of the subtree what the largest frequency is. If it doesn't include the entire subtree, you have to actually dig in deeper before you figure that out. Is that clear?
Okay, so for instance, the question you asked, the one between 10 and 16.
Yeah, so let's do that. So for 10 and 16, so if I want between 10 and 16, here's what I'm going to do. I start there. 10 and 16 both are to the left of it, so I ignore that node. I come down here, and 10 is on one side, 16 is on one side. So that's actually an interesting node. But all I need is the frequency of this guy that I have to keep track of. There is no subtree that I have to worry about. So I'm going to go down and look for 10, and I find it right there. So therefore, so far, the most frequent item is number 10, and its frequency is 11. Okay. Then I go to the right side, but here, 15 is within the range, but then this entire subtree is not, and I can quickly figure that out. Right? So therefore, I have to dig in deeper, and one of the things I'm going to do is find its frequency, which currently is the highest, and so I update the 11 to 14. Then I'm going to look at the subtree here, figure out that this entire subtree is in the right range, and I will figure out what is the largest or the most frequent item in that subtree. And I don't have to go through that entire subtree, but I'll know that answer as 7.
Which you would know even faster 12 because 12.
Exactly, yeah. So in the end, it's a maximum between 11, 14, 3, and 7. And answer is 14, and I'd have it. So either I'm looking at entire subtrees, or I'm looking at nodes on my path, and I just answer that. Okay, so this is a simple frequency problem. But you can actually complicate this even more. It's more tricky if I ask you for a. Actually, yeah, this is a slightly different problem. Okay, so and I call this a simpler problem. I'm not sure. So it's a different problem. You're given a set of items. They're not in any sorted order. And again, I'm going to give you a range, and I'm going to ask you what is the largest item there.
The most frequent one or the largest?
The largest. There is no frequency here. Okay. Again, there are two ways of thinking about this. You could think of this as a two-dimensional range problem, where one dimension is the index, and the other is its value. Right? Because I'm going to ask you a certain range, and I'm going to say what is the largest one. So you find the range, and for each of those subtrees, you go over there and find the largest. Okay, that's one way to do it, but I don't think it's going to be competitive there. There may be a log squared thing, although you may be able to improve it. But you can turn this into something like a range query, where, or you can think of it from scratch as, what extra information should I store in each node in order to solve this problem? So I'm going to continue this next time. I need to go back and I have to attend a meeting, so I need to stop here. It's 4:50 anyways, right? So we'll talk about this. I can share the